Okay, in this video, we're going to be looking at other sets, operations, and their properties. So what we'll be looking at, we'll continue our discussion with sets, but we're going to be looking at set intersection, set union, and set difference. Also, some of the properties of set operations. Also, we'll be using Venn diagrams as a problem-solving tool, and we're going to be using sets to come up with the Cartesian products of sets. Okay, we'll begin our discussion with set intersection. You want to consider the following sets. C is a set of all x such that x is a college graduate, and S is a set of all x such that x earns at least $40,000. And suppose we want to mail a questionnaire to all individuals in a certain city who are college graduates and who earn at least $40,000. Then the individuals to receive the questionnaire include those common to both sets C and S. So this is just a application of what set intersection means. And here in this case here, again, C is a set of all x such that x is a college graduate, and S is a set of all x such that x earns at least $40,000. So here the intersection of sets C and S is going to be this shaded region. Okay, so here you can see that shaded region. That means the intersection of both C and S. You're dealing with those who are college graduates and earn at least $40,000. And this is the formal definition of what an intersection is. The intersection of two sets A and B, and it's going to be written as A with an upside down U, then B. That means A, the intersection of A and B. That's a set of all elements common to both A and B. And in set builder notation, we can write that as the set of all x, such that x is an element of A and x is an element of B. And the key word for the intersection is and, which means that both conditions must be met. Okay, both conditions must be met. So in this example, we want to find the intersection of A and B. And in part A, we got A, which has the elements 1, 2, 3, 4. B having the elements 3, 4, 5, 6. So the intersection of A and B would be those elements that are in both A and B. In this case, the number 3 is in both A and B, and 4 is in both A and B. So the intersection of A and B will be the elements 3, 4. Because both of those elements are in both A and B. Now part B, we got A, which has the elements 0, 2, 4, 6, and so on. B has the elements 1, 3, 5, 7, and so on. So here we want to find the intersection of A and B. We want to find those elements that are in both A and B. Notice, this has the set of even numbers. This set has the set of odd numbers. There's nothing in common in both of these sets. So here we use the empty set, which is a circle with a slash. That means the empty set. And that means that sets A and B are what we call disjoint, meaning that A and B have no common elements. Part C, A has the elements 2, 4, 6, 8, and so on. B has the elements 1, 2, 3, 4, and so on. Now we want to find the intersection of A and B. Notice that all the elements in set A, even though it's an infinite set, are common in B. Because in set B, you have the natural numbers. Set A has a set of even numbers. Your natural numbers does contain your even numbers. So the intersection of A and B would be simply set A. Because set A has the set of is also common with the set B, which is a set of all natural numbers. So in this case here, let's say if C represents the individuals with a college degree and S represents the individuals earning at least $40,000. We can use what we call a Venn diagram to display this information. Okay, now let's take this a little bit further, because we already talked about how to do a Venn diagram to represent the intersection in this particular situation. If we know that 4,800 individuals have college degrees, 5,400 earn at least $40,000, and 1,200 have a college degree and make at least $40,000. So let's look at this situation here. 1,200 of them have a college degree and make at least 40,000. Notice that 1,200 goes in this shaded area right here because that represents those who have a college degree and make at least $40,000. Okay? We know 4,800 of them have college degrees. So subtract the 1,200 from the 4,800. That would represent this part, which is 3,600, because this entire circle represents 4,800. 1,200 of them are common. Subtract the 1,200 that's in common from the 4,800, you'll get 3,600. And we know 5,400 of those 5,400 people earn at least $40,000 and do not have a college degree. So this right here, this circle right here that I'm outlining represents the 5,400. We know the 1,200 have a college degree and earn $40,000. So the others will be, subtracting the 1,200 from the 5,400 will be 4,200. Okay, that's how we do the Venn diagram in this particular situation. Okay, let's consider the same situation for college graduates and those making at least $40,000, those same two sets. Now, suppose we want to mail a questionnaire to all individuals in a certain city who are college graduates or who earn at least $40,000 or both. Then the individuals to receive the questionnaire include those who are members of Set C or Set S. Okay, so this illustrates the union of these two sets. And this is what the union looks like. That's the shaded region. Okay, that's all the college graduates and all those who make at least $40,000 a year. Okay, so that's the union of Set C and S. Okay, and here I have the formal definition of what a union is. The union of two sets A and B, which is written as A, and this is the symbol for the union, which is like a U. A union B, that's the set of all elements in A or in B. In set builder notation, we can write this as a set of all X, such that X is an element of A or X is an element of B. That's the union of A and B. Now, here we're using the word or. Now, we're going to be using the inclusive or, and that implies one or the other or both. That's what we mean by the inclusive or, because we're dealing with one or the other or both. So if we want to find A union B, or the union of sets A and B, let's say part A has A with the elements 1, 2, 3, 4. B has the elements 3, 4, 5, 6. The union, we put the two together to get this. A union B will be 1, 2, 3, 4, 5, 6. Okay? And we write each element only once. Even though 3 and 4 are in both A and B, we still write each element only once. Part B, A has the elements 0, 2, 4, 6, and so on. B has the elements 1, 3, 5, 7, and so on. We want to find the union of A and B. In this case here, it'll just be 0, 1, 2, 3, 4, and so on. That's the set of even numbers for set A. This is the set of odd numbers for set B. The union of the two is the set of whole numbers. And part C, A has the elements 2, 4, 6, 8, and so on. B has the elements 1, 2, 3, 4, and so on. Now the union of A and B would just simply be B, because Set A just has a set of even numbers. B has a set of natural numbers. Your even numbers are in the natural numbers. That means every element of A is in B, so the union of A and B would just simply be B in this particular situation. Now, set difference is this. You want to consider the following sets, which is the same two sets that we talked about at the beginning of this video. Now, the set of individuals earning at least $40,000 but not a college graduate is called the complement of C, relative to S, or the set difference of S and C. Okay. And the complement of A relative to B, written as this, and this is not read B minus A. That's going to be the set of elements in B that are not in A. So here, the complement of A relative to B would be the set of all X, such that X is an element of B and X is not an element of A. Okay. Now keep in mind the minus sign is nothing but an operation on numbers, and set difference is an operation on sets. So we can call this a set difference. Okay, and that relative complement is this. You take away all the elements in A. That's the set difference between B and A, and that's the same as saying the intersection of B and the complement of A. So you're removing the complement of A. And it's going to be this. So this represents the set of all elements in B that are not in A. Okay, so in this case here, if A is equal to has the elements D, E, F, B has the elements A, B, C, D, E, F, and C has the elements A, B, C, D, we start by doing the set difference of A and B. That's A, and that's B. Okay? So if you take away everything that's in A, you're going to be left with the empty set. And then the difference between B and A, here's B, take away the elements that are in A, which is your D, E, and F, you're going to be left with A, B, C. Okay, then the set difference of B and C, here's B, take away the elements that are in C, which is A, B, C, take those out, you're going to have D, E, F. And then the set difference of C and B, here's C, that's B, take away any elements that are in B, A, which is A, B, and C, you're left with the empty set. Okay. Properties of set operations is the next thing we'll look at. The first thing is the commutative property. For all sets A and B, the intersection of A and B is the same as the intersection of B and A. And the union of A and B is the same as the union of B and A. Since the order of the elements in a set is not important, it does not matter in which order we write the sets and when we find the union or the intersection. Okay. So this is what the commutative property with set operations is. The intersection of A and B is the same as the intersection of B and A, and the union of A and B is the same as the union of B and A. The associative properties looks like this. I can take the intersection of A and B, and then whatever that is, get its intersection with A. That's the same as taking the intersection of A and B, and whatever that is, get its intersection with C. And this also holds true with the union. Take the union of B and C, whatever that is, I can do the union of that with A, or take the union of A and B, whatever that is, I get its union with C. Since the order of the elements in a set is not important, it does not matter in which way we associate sets when we take the union, or the intersection. And later on in this particular course, we're going to be talking about those two properties, the commutative and the associative properties, when we deal with addition and multiplication. Okay, now the distributive property of the intersection over the union is this. The intersection of A and the union of B and C is the same as the intersection of A and B, or the union of the intersection of A and B and the intersection of A and C. Okay, that's the distributive property of the intersection over the union. You take the union of B and C and get its intersection with A. That's the same as this, the union of the intersection of A and B and the union and the intersection of A and C. Okay. Okay, now I won't be going over these with you, but we are going to talk about Venn diagrams. Okay, so here we're going to be using Venn diagrams as a problem-solving tool. In this case, here, suppose M is the set of all students taking mathematics and E is the set of all students taking English. Identify the students described by each region in the figure. Region A contains all the students taking mathematics but not English. This is what region A is. Those that are taking mathematics but not English. Now region B is the one in the middle. That contains all the students taking both math and English. And then what region C is, that's those that are taking English but not mathematics. Okay, so that's what region C is. All students taking English but not mathematics. That's this region right here. Now region D, that's this part on the outside, that's all students taking neither math nor English. Okay, so that's the representation of a Venn diagram. In fact, one of your problems in your homework and on the writing assignment will be dealing with Venn diagrams and how to come up with the correct numbers in that Venn diagram. Take a look at the situation here. In a survey of 110 college freshmen that investigated their high school backgrounds, the following information was gathered. 25 took physics, 48 took mathematics, 10 took physics and mathematics, 8 took biology and mathematics, 8 took physics and biology, 8 took all three subjects, 45 took biology. Okay, so that's the situation that we have here. And we want to create from that situation a Venn diagram and answer these questions. How many students took biology but neither physics nor mathematics? How many took physics, biology, or mathematics? How many did not take any of the three subjects? Okay, so here we're going to build a model using sets, or in this case a Venn diagram. Now P is going to be the set of students taking physics. B will be the set of students taking biology. M is the set of students taking mathematics. In this case here, the shaded region represents the 5 students who took all 3 subjects. So sometimes you have to work backwards. If you recall, one of our strategies for solving problems is to work backwards. In this situation, this is what we're doing here. We're working backwards. We know that 5 took all 3 subjects. So that shaded region is going to be the 5, because that's the intersection of all 3. Now the lined region is going to be the students who took physics and mathematics but did not take biology. Okay. See where this 5 comes from? We know 5 took all 3. But we know 10 took physics and mathematics. So if you subtract 5 from the 10, you're going to get this 5. Okay. Now, so here the number of students who took biology but not physics or mathematics is going to be represented by In this case, B minus the union of P and M. Okay, so in this case here, 10 students took physics and mathematics, and 5 also took biology. That means that 10 minus 5 will be equal to 5. That means that the 5 students took physics and mathematics, but not biology. So that's where this 5 comes from. Okay, on the next slide. 8 students took biology and mathematics. 5 took all 3, so subtract the 5 from the 8, you're going to get 3. That's where this 3 comes from. Okay. That's the 3 that took biology and mathematics, but not physics. And then, if you subtract 5 from the 6, you're going to get 1 student that took physics and biology, but not mathematics. Because in the problem it tells you that 6 took physics and biology, so that's where this 1 comes from. And then to find the number of students who took biology but neither physics nor mathematics, we subtract 45, which is the total number of students that took biology. That's this right here. Okay, and we subtract, and we count up the distinct regions here, like the 1, the 5, and the 3. That gives us 9. Add those up, that give you 9. Subtract 45 minus 9, you're going to get 36. So we know 36 students took biology, but neither physics nor mathematics. And the number of students that took physics, but neither mathematics nor biology, here it is. Add 1, 5, and 5, that's 11. Subtract 25 from 11, you're going to get the 14. That's where this 14 comes from. So we know 14 students took physics, but neither math nor biology. And then the number of students that took math, but neither biology, that's this circle down here. Down here, add 5, 5, and 3, that's going to give you 13. Subtract the 13 from the 48, you'll get 35. Okay, so that's how you will complete a Venn diagram from this particular situation. Okay, and do be familiar with that, because one of your writing assignments does have something that is related to completing a Venn diagram. Also in the homework, you'll have some Venn diagram type problems like this. So do be familiar with that. Okay, and to continue on, the number of students who took physics, biology, or mathematics will be this. 35 plus 14 plus 36 plus 3 plus 5 plus 5 plus 1, which will be 99. In other words, we're just simply adding each of these individual numbers that you see inside those circles. And the word or means you're putting all of them together. So that's 99. But 110 students were surveyed. So we want to find out the number of students that didn't take any of these 3 subjects. So take that 99, subtract that from 110, you're going to get 11. And 11 will be on the outside. So in this case here, 11 students did not take any of the 3 subjects. Okay. All right, the next thing we're going to talk about is Cartesian products. One way to produce a set from 2 sets is forming pairs of elements of one set with the elements of another set in a specific way. Okay, so we're going to look at Cartesian products here. Suppose a person has 3 pairs of pants, where P is going to be the elements blue, green, white, and 2 shirts. S is going to be blue and red. According to the fundamental accounting principle, there are 3 times 2 or 6 possible ways to pair an element from set P with an element from set S that's forming a set of ordered pairs. Now, we talked about the fundamental accounting principle in this in one of the videos here. So here, if one situation can be done m ways, the second one can be done n ways, then m times n ways can be performed using that fundamental counting principle. And this is what the Cartesian product looks like. The shirts are going to be red and blue on this side. The bottom is the pants, blue, white, green. Okay, because the first component in each pair represents the pants, and the second component in each pair represents the shirts, the order in which the components are written is going to be important. Because blue will be paired with blue, like this. Then blue will be paired with red. Then white is paired with blue. White paired with red. Green is paired with blue. And green is paired with red. So here, order is going to be important in this particular case. And also the equality for ordered pairs. The ordered pair XY is equal to the ordered pair MN if and only if the first components are equal and the second components are equal. A set consisting of ordered pairs is an example of a Cartesian product. Okay. For any sets A and B, the Cartesian product of A and B is written as A cross B. That's how we read this, A cross B, not A times B. It's read A cross B. That's the set of all ordered pairs such that the first component of each pair is an element of A and the second component of each pair is an element of B. In set builder notation, A cross B will be the set of all ordered pairs XY such that X is an element of A and Y is an element of B. Okay. Look at some examples here. If A has the elements A, B, C, and B has the elements 1, 2, 3, find each of the following. Part A is A cross B. So here we're looking at set A, which is A, B, C, and B, which is 1, 2, 3. We start off with the first element in A, which is A, and pair it with each element in B. So A will be paired with 1, so we have A1. A will be paired with 2, so that's A2. A will be paired with 3, so that'll be A3. And then for B, pair each element in set B. B will be paired with 1, so you have B1. B is paired with 2, so it'll be B2. B is paired with 3, so you have B3. And the same thing for C. You're going to pair that with each element in B, so it'll be C1, then C2, and C3. So those sets of ordered pairs represent the Cartesian product of A and B, or A cross B. Now B cross A, which is part B, is going to be a little bit different because now B will be the first element. Each element in B will be the first element. Each element of A will be the second. So now 1 will be paired with A, so you're going to have 1A. 1 will be paired with B, so it'll be 1B. 1 will be paired with C, so it'll be 1C. Then 2 will be paired with A, so it'll be 2A. 2 will be paired with B, which will be 2, B. 2 is paired with C, so it'll be 2, C. And the same thing with 3. 3, A, 3, B, 3, C. So you do see a difference between A cross B and B cross A. Now part C, A cross A, that means the Cartesian product of itself. That means A will be paired with itself, that's A, A. A will be paired with B, that's A, B. A will be paired with C, A, C. Then B will be paired with A, so that's B, A. B is going to be paired with itself, B, B. And B will be paired with C, B, C. Then C will be paired with A, which is C, A. C will be paired with B, which will be C, B, I'm sorry. And then C is going to be paired with itself, C, C. That's what we mean by the Cartesian product of itself. Okay. It is possible to form a Cartesian product involving the null set, or the empty set. Suppose A has the elements 1, 2. Because there are no elements in the empty set, no ordered pairs x and y, with x being an element of A and y being an element of the empty set. You'll have no elements in that empty set. So that means that A cross the empty set is the empty set. And on a similar note, the empty set cross A is also the empty set for all sets A. Okay, so that will conclude this particular video on other set operations and their properties.